right, good evening, everyone, and welcome to International Observe the Moon Night. So we have an amazing event tonight. I know for some of you are in parts of the country that sadly are clouded out or rained out, so hopefully a little bit of San Antonio can come to you to be able to observe the moon. So let me share a little bit of information with you about the moon, and then we'll have some of our amazing guest speakers do their presentations tonight. So a little bit about some lunar fun facts. The moon is roughly about 1/4 the size of the Earth. So to give you kind of a rough size comparison, think of like a baseball to a basketball size comparison. And even though our moon is relatively small compared to the Earth, it is the 5th largest moon in the entire solar system. So we have a pretty decent sized moon to go around. And it's also the 2nd densest moon compared to Io, which is the 1st. But, you know, we got a good moon. Believe it or not, the moon is mostly dark. It's kind of like asphalt, but since our sun is so big and so bright, it reflects very easily. And there are moonquakes, and the moon came from the Earth. In fact, there are theories that back in the ancient times, something about the size of Mars smacked into the Earth, a chunk of the Earth popped off, and that section started to coalesce into a sphere to create our moon. And I'm sorry, Pink Floyd fans, there is no dark side of the moon. In fact, the far side of the moon is what astronomers call it, is actually very, very bright. So I'm sorry to break the bearer of bad news. Also, another fun fact, our moon is drifting away from us, about 3.8 centimeters per year. So nothing to worry about over the long haul. In fact, just to give you kind of a front and backside view, as I mentioned, the backside of the moon, the side we don't see, is very, very bright. But on the front side we see is those dark areas, which are called maria, which is Latin for the term seas or oceans. Now, the ancient miners didn't believe that there were oceans on the moon, but they thought they looked like oceans, but in actuality, they're old ancient lava flows. So why is it we only see one side of the moon? Well, our moon is what is known as in a synchronous orbit, or tidally locked. So we always see one side of the moon always facing us at all times. So it rotates at the same rate it goes around the Earth, which that rate is roughly around about 27 days, or 29 days if you want to compare it with its position to the sun. So hence why our months have 30 days, because they come from the Old English word moons. So if there's something you want to do for fun, well, if you can go out and look for the moon, look for shapes in the moon. You can look for the man in the moon, the woman in the moon, there's a rabbit in the moon, there's a tree in the moon, there's even handprints, and many more. So if you want to check those out, by all means, have some fun making some art in the different faces on the moon. And just to give you a rough idea, you can take this image and take a picture of it, and you can compare it to the actual moon. And this is where the Apollo lunar landings are, with the hope of, in the future, we're going to have Artemis coming up in 2024. Yay! We're going to land women on the moon. Huzzah! So what can you do during this time while you're celebrating International Observe the Moon Night? Well, believe it or not, if you are an artist, we would love to see your artwork. If you have poems or haikus, send them our way. You can even post them on our Facebook at Scobee Educaiton Center with the hashtag International Observe the Moon. There's also fun activities. If you wanted to make it a monthly event, observe the moon for a whole month. Tell us what you know. And also, if you want to do something really fun, I like bingo. So if you want to have some bingo challenges with some of your friends, challenge them that they have to fill out all the bingo to get a prize. And also, if you want to get some lunar certifications through the Astro League of the Pacific, they have some certifications that are professional to where you can observe the moon and get a nice certificate for doing so. But if you're looking for more, check out NASA's webpage at International Observe the Moon Night, and you can see all sorts of fun activities that you could do with your family and kids and everything. So what I will do is I will stop sharing and I will introduce our first guest speaker. Just bear with me here. Having to do a setup here. There we go. So our first guest speaker is Lizeth Magana, and she is a part of NASA's Lunar Reconnaissance Orbiter mission, and she is a Ph.D. candidate at University of Texas at San Antonio. And as a part of the LRO team, she analyzes ultraviolet images on the moon in search for water ice on the moon. So, potential Dr. Lizeth, could you kindly take it away, share your screen, and tell us more about ice on the moon?
All right. All right, as Michelle noted, my name is Lizeth Magana, and I'm here today to tell you about ice on the moon. And what you may be thinking is, what? There's ice on the moon? And I'm here to tell you that yes, there is. Even though we normally think of the moon as being a really dry and dusty place, so much so that the Apollo astronauts actually complained about all the dust on the moon. I'm actually here to tell you about the different types of ice on the moon and where we can actually find it. As she mentioned a little bit about myself, I am a graduate student right now at the University of Texas at San Antonio. I'm actually just starting my 5th year, and I work with the Lunar Reconnaissance Orbiter team at the Southwest Research Institute. So to start, I have here a picture of the moon, and if you observe it later tonight, if you go outside or look out your window, this is what you should see tonight. So we have the familiar Mario regions that Michelle was talking about, and these are these dark regions. And then we also have the highlands that are really bright. But what we don't see from this image is any water. And that makes sense, right? The Apollo astronauts didn't go to the moon and splash around in puddles, right? That didn't happen. So in order to see the ice on the moon, we actually need to go to either the North Pole or the South Pole. And tonight I'm going to walk you through the South Pole, but you can think of the North Pole as an analog, right? Whatever happens at the South Pole, it's going to be the same in the North Pole. So as we zoom into the South Pole here, we start to see a lot more of these craters, and that's because the surface of the moon is just riddled with these craters. Now, as we keep zooming in, we start to see that some of these craters are dark. And this video was showing in the light regions, this is where the sun is illuminating the surface, and everything that's dark is where the sunlight is not illuminating it. So these regions are in shadow. So we're zooming in here on one specific crater, and this is Shackleton crater. And it is almost exactly at the South Pole of the moon. Now, as we keep zooming in here, we're going to start to see some time pass, and we'll see how the shadows change. So as time passes, you know, the moon is going around the sun, or it's going around the Earth, which is going around the sun. And we start to see that the regions that are illuminated shift throughout the year. But the regions that are dark in the center of these craters don't change much. So specifically looking at Shackleton crater, the very center of this crater stays dark even though time is passing. And these regions that are in shadow are then called permanently shadowed region. That makes sense, or PSRs. Now what I'm showing here on the left side of the screen is a temperature map of the South Pole. Everything in blue or in purple that's outlined in this black color, these are the permanently shaded regions. And we see that 3 of them stick out in particular. These are Hayworth, Shoemaker, and Faustini. They're really large circular craters toward the center of this map, so toward the center of the South Pole. And you'll see these come up throughout the rest of the presentation, so you can keep an eye out for these. And these are actually some of the most studied permanently shadowed regions. In the top left corner, we also have Cabeus crater, which we'll talk about more on the next screen. It's very important. Now, since I said that these regions are in permanent shadow, they don't get much sunlight, you can imagine that they remain very cold. How cold is that? Well, they are actually some of the coldest regions in the solar system. And you may be thinking, well, what about Pluto? You know, it's so far away from the sun and it's covered in ice. Well, the minimum temperatures on the surface of Pluto that we know of go down to as low as 40 Kelvin. That is negative 387 degrees Fahrenheit. Some of the coldest regions within these permanently shadowed regions get as cold as 35 Kelvin. That is negative 397 degrees Fahrenheit. So that's a whole 10 degrees Fahrenheit colder. And how cold is that exactly? Well, if you were to somehow go inside one of these PSRs without any protection, your entire body would freeze solid in less than 2 minutes. So these regions are actually so cold that they can retain water ice for billions of years. But that's if the ice can make it there in the first place. So how does the water get there? Well, we think the water could be delivered to the lunar surface throughout 3 mechanisms. The first of which is either through a comet or meteoroid bombardment. So you can think there's this rock traveling through space, and it's literally covered in ice. And when that hits the surface of the moon, it's going to release all of that ice. Secondly, we think it may be coming from the inside of the moon. So the moon is outgassing some of this water, or it could have came out through eruptions a long time ago. And third, we think that it could be actually forming on the surface of the moon. So the sun is ejecting off these charged particles, this hydrogen, and it's hitting the surface of the moon. And when it interacts with the oxygen that's on the surface, it could be creating H2O. Now, what happens when the water is on the surface? How does it actually get to the poles? So once we get this water onto the surface of the moon, it can actually hop. So it follows these parabolic trajectories to the South Pole. But that's only if it isn't lost to space. So as we mentioned, the moon is only about 1/4 of the size of Earth, and its gravity is about 1/6 of what it is here on Earth. So it's actually really hard for the moon to hold on to any gases. It doesn't actually have an atmosphere like we have on Earth. What it does have, though, is what we call an exosphere. And that is a very, very, very thin, almost atmosphere. And so when these particles are jumping on the surface, there's not much gravity to hold them there. So they could either get lost to space, but every now and then they do make it all the way to the South Pole. And then, like I mentioned, it is so cold there that these particles cannot move. It's so cold, so they just get trapped within these PSRs. And this is an idea that we've had since like the 1950s. But we actually didn't get to test this idea until 2009. So in 2009, we launched LCROSS and also the Lunar Reconnaissance Orbiter, or LRO. We'll talk about more about LRO on the next slide. But here, so we strapped LCROSS and LRO onto this rocket, sent it off toward the moon. Once it got close to the moon, we ejected the last stage of the rocket. So we just sent it and let it fall onto the surface of the moon. And you can, imagine dropping a bowling ball on the surface of the moon. What happened? Well, we had this plume of debris just come flying out. This plume was so big. You can imagine if you're standing on the surface of the moon, looking up at it, it was about 3 to 5 miles high. So that's about 20 Empire State Buildings tall. If you've never seen the Empire State Building, I haven't either. You can think about this being as tall as 4,000 people standing on top of each other. And now this was really exciting because what we measured inside of this plume was a lot of water, a lot of H2O. But we also measured CO2, carbon dioxide, carbon monoxide, ammonia, and a lot of other ices. Now, I said we also launched the Lunar Reconnaissance Orbiter at this time in 2009. And LRO was meant to be the first steps in a program to extend the human presence in the solar system. But eventually, it actually took on more of a science focus. So we have 5 primary objectives that we're investigating with LRO. The first one is the impact history of the moon. So this is looking at the craters on the surface of the moon. Secondly, we're looking at the lunar geologic processes. This includes the volcanism that took place a long time ago. Also looking at the formation of the lunar regolith. This is the lunar dust that I was talking about that the Apollo astronauts complained about. And this is a really, really fine dust. You can think about this as this consistency of like powdered sugar or flour. And it literally covers the entire moon. Fourth of all, and this is the one that we're going to be focusing on today, is we are looking at volatiles on the moon, and especially at the poles, so the North Pole and the South Pole. Now, volatiles is just a fancy word of saying if this compound was on Earth, it would easily just sublimate. But since it's at the moon in the PSRs, it's actually a solid, so it's ice. So this is going to be referring to H2O ice, CO2, so water, carbon dioxide, ammonia, etc. And then lastly, we are looking at the lunar radiation environment. So what is the radiation on the surface of the moon? So I mentioned to you that PSRs are called PSRs because there is no direct sunlight going into these craters. So how is it that LRO is looking at these volatiles on the moon? How is it that we're actually able to see these volatiles inside of the PSRs? Well, there were some scientists at the Southwest Research Institute that were actually really clever. So if you think about going outside in the middle of the night, say in the country away from a city, so you don't have any city lights, but you still have some illumination, right? The sun isn't out, but we have reflections off of the moon. But what else do we have in the night sky? We have stars. So LAMP, the Alignment Alpha Mapping Project, is an instrument that is actually able to use the ultraviolet light coming off of these stars to look inside of these permanently shaded regions. So as LRO orbits the moon, it's able to measure the reflected light from the moon. So these stars are in the sky, they're shining UV light, it's hitting the surface of the moon, it's being reflected back out, and as LRO goes around the moon, it measures the reflected light. And this allows us to look inside the PSRs. Now, as LRO goes around, it measures the surface as a sort of push broom fashion as we're seeing here. So the area that it's looking at is actually about 250 meters by 250 meters. But as it travels across, it is 250 meters wide across the entire moon. And then as LRO goes around the moon, its orbit doesn't change. But what does change is the surface that it's looking at. So the moon is orbiting. So as LRO goes around, it's looking at a different footpath every single time. And we can add them together, as you're seeing here on the left, to look at the entire surface of the moon. And this allows us to create maps of the moon in the ultraviolet. And that's what we're looking at here on the right side of the screen. Once again, we can see Hayworth, Shoemaker, and Faustini kind of stand out. So here we have a albedo map is actually what we have. And it's the ratio of the light hitting the moon to what's going back out. And we can create these maps in any UV wavelength that we want, between say 57 nanometers and 200 nanometers. And the two wavelengths that we're interested in the South Pole to look for ice are actually what we call the on band. This is between 130 and 155 nanometers. And the off band, this is 155 through 190 nanometers. And why do we care about these two wavelengths? Well, what I'm showing here on the left side of the screen is a reflectance plot with wavelengths. So we have reflectance here on the y-axis and wavelength on the x. In black, we have the reflectance of the lunar regolith, right? Just dry lunar regolith, no water on it whatsoever. But once you add a tiny bit of ice, we see the curve that's here in red. And we see that in the on band, the red curve and the black curve are almost equivalent, meaning that in the on band, we have really weak water reflectance. That is, if you were to have regolith with ice on it, it would look really similar to regolith without ice on it. Now in the off band, it's a completely different story. We see that the red curve kind of skyrockets, meaning that if you have regolith with just a little bit of ice on it, it's actually going to be really reflective. So we say it has a strong water reflectance. So if you have regolith with just a little bit of ice on it, it's going to look really bright compared to the regolith that doesn't have any ice on it. And then we are able to create these albedo maps in both of these wavelength regions, both in the on band, that's in the top right corner, or the off band in the top right corner, and the on band in the lower right corner. So when we take the ratio of these two, so we're taking the ratio over water ice would be bright to where it would be dark, we get the off to on band ratio, which is then a signature of water ice. When it's high, that is on the map on the right, where we see the blue color, this means that it is consistent with the presence of water ice. Now, what we notice is that where it's blue, where we might have water ice, correlates really well with where we have these permanently shaded regions. That is, we only see the blue color inside of these PSRs. We don't see hardly any blue outside of these PSRs. And why is that? It is because the regions outside of the PSRs are hit by direct solar illumination, which means they heat up and they actually get warm enough that the water would either sublimate away, be lost to space, or it would move somewhere else, maybe somewhere colder, maybe another PSR. And by analyzing the water inside of these PSRs, we have actually found that there may be up to 2% water ice by mass. But I also mentioned, for example, within Cabeus, we measured a whole bunch of ices. And are there these other ices within these other PSRs? That is actually the focus of my thesis as a graduate student. So what I'm showing here on the right is where the off to on band ratio is high, that is these green diamonds. And then we have temperature on the y-axis and the different PSRs I have across the x-axis. And these are only 6 of the PSRs that I chose to study. Now, based on the temperature of where these high off to on band ratios are, that might tell us a little bit about what kind of ice we're detecting. So the ammonia ice, NH3, and carbon dioxide ice, CO2, have a similar signature. When they're present, they have a high off to on band ratio. So also on this plot here, I'm showing the shaded green/blue region. And this is where water ice is stable for billions of years. So where it's shaded in green, where these high off to on band ratios are, this is consistent with water ice. Now in the light purple, this is actually where these one population of high off to on band ratio that we have here is consistent with both water ice and ammonia ice, meaning that both water and ammonia would be stable within this temperature region for billions of years, allowing them to accumulate. So how do we know if we're detecting ammonia or water within this region? And the truth is that we don't really know, and we won't know without any modeling, which is work to come for later on in my thesis. Now, if we had any high off to on band ratio in this dark purple region, this would be consistent with both water ice, ammonia ice, and carbon dioxide ice. But we don't actually have any high off to on band ratio in this region, at least not in the 6 PSRs that I chose to study. But what we do see here is that there's an abundance of resources at the South Pole. For this reason, the South Pole was selected as a future landing site by Artemis. Now, Michelle mentioned a little bit about Artemis in the introduction. And Artemis is actually a NASA mission, and they're partnering with many commercial partners to actually go back to the moon. And we want to land the first woman and the next man on the moon by 2024. But not just that. We also want to develop an Artemis base camp at the South Pole in order to support longer expeditions on the lunar surface. And this is in hopes that we can eventually do this on the surface of Mars. Now, just to summarize, what have we learned during this talk today? We learned that the moon has some of the coldest places in the solar system, and they're known as permanently shaded regions. And that these regions are so cold that they can actually retain volatiles for billions of years. We learned that we have actually detected water ice and a variety of other ices within at least one PSR, Cabeus. But we have also seen evidence of these ices within other permanently shadowed regions. And lastly, we saw that we have resources at the South Pole that can be used during future manned missions to the moon. And with that, I will take any questions.
All right, thank you, Lizeth, so much for that wonderful presentation. So now is the opportunity to ask her any questions. So go ahead and head into the Q&A section down below and type in questions that you might have for her, and we would be happy to toss them her way so you can answer her. Any questions whatsoever?
So while we wait for questions, one question that I do sometimes get is how can these resources, or how could the volatiles be used as resources, right? How do we actually use these ices in future manned missions? Answer to that is you could use, if you are able to get the water, you could use the water to drink, first of all. You could use it to grow any crops that you're trying to grow. You could break it apart, get oxygen to breathe. These are just some ways that you can use the resources if you're able to get to them. Of course, there's probably more that I haven't thought of.
All right, so we do have one question. What inspired you to center your career around the moon? What was it that inspired you to look up to our moon and say, okay, I want to study that?
Yeah, so the reason that I wanted to study the moon and is specifically for these PSRs, right? So as far as we knew is that there's water within these PSRs. We knew that once I started my PhD project, and we knew that there were resources within Cabeus, but what we didn't know was whether there were these other ices within these other PSRs, and that was really what I was interested in. Are these resources spread out through all of the PSRs at the South Pole, and really using those for future manned missions? That was kind of my objective.
Okay. Any other questions? Just in case if you're unfamiliar with Zoom, I know it's a new technology that we're slowly learning for many of us. Just simply scroll down with your mouse and there's a bubble that looks like Q&A and type in there and you can type in on your questions. All right, so we got a question. It said, what is the future of lunar exploration at NASA going to look like?
That's a good question. Specifically, lunar exploration was the question.
Yeah, will it be like something like human exploration from here on out, or will it be like the next gen LRO? Or is it going to be a mix?
Yeah, it'll be more of a mix. We do have another orbiter going up, I believe. We have some rovers. For example, Artemis is wanting to send, I believe it's the Viper rover, sort of to explore the terrain at the South Pole. You know, before we actually send people up, we want to know what to expect. And then, yeah, eventually, you know, 4 years from now, we want to have people on the moon. So the future of lunar exploration is shifting toward people, I think. But, you know, still retaining the orbiters and retaining the rovers.
All right, next question. How do you imagine humanity utilizing the water found on the moon?
Yeah. So as I mentioned, the water is really important because it can be used to, say, power the lunar base that you built on the South Pole. It can be used to supply the oxygen that you're breathing while you're at the South Pole, and even provide water for you to drink while you're there. So it's important to be able to get this stuff while you're on the moon, because it's really expensive to send it from Earth to the moon, right? It's probably going to be cheaper to be able to access the water while you're there for these day-to-day things that you need. For example, oxygen to breathe.
Okay, we do have a question coming from a young viewer, and they are asking, how does the water hop?
That's a good question. So as I mentioned, the moon doesn't have much gravity, which means that most of the gases on the moon are lost. So they're moving upward, and if they move upward fast enough, they're gone. But you do have that gravity that's pulling it back to the surface. So that creates sort of these parabolic hops that maybe eventually they'll get to the South Pole of the moon.
Okay. So next question is, how do you think we can feasibly use the water trapped at the poles to support something like human bases at the moon?
Yeah, so a lot of this is you know, engineering. How do you get the water ice out in the first place, which is not really my area of expertise. But again, once you get it out, if you can find a way to break it apart, create oxygen to breathe, or use it to water your crops or drink it, stuff like that.
So would they have to have like some type of filtering system for that, I presume?
Probably, yeah. Yeah, as I mentioned, that's more of the, you know, engineering aspect of it that I'm not as familiar with.
Okay, next question. How big is the base that they plan to build on the moon?
I'm not really sure, actually. That's a good question. I don't know how big it would be, or, you know, how many people it can sustain. But yeah, I know the plan is to create a base, and, you know, launching off of the moon to explore other regions is a lot cheaper than launching off of the Earth, for example, because they have less gravity. I don't know if that's, you know, the plan of the Artemis base, but yeah.
Okay, so kind of a question for our younger audience members.
Mhm.
What would they have to do what you do? Starting from elementary, so you got this elementary school student in 4th grade, and they want to do exactly what you do. What do they have to do?
Yeah, so my, you know, bachelor's and master's degrees are in physics. That's one route to take. You can study planetary science, or lunar geology, or geology. You can, you know, apply that to lunar geology. But then just get involved with NASA missions, which you can do, you know, later on in your career. So just study science, be interested, ask a lot of questions.
Okay. Another question we get from Facebook is, what is the most interesting thing you have learned? from your studies?
Yeah, let's see, the most interesting thing I have learned. Let's see, something interesting I've learned is that it's hard to really tell if you're looking at water ice or different ices. You know, it's hard to really determine what it is that you're looking at, a little more so than I expected. So that really takes all of the modeling aspect that I haven't done yet. But yeah, the most interesting part was that there's all this cool stuff at the moon that we can use for our own benefit.
Okay, next question. Is there a difference between the North Pole and the South Pole of the moon? Like in terms of craters, in terms of possibly water? What is the difference?
Yeah, so as I mentioned, there's permanently shaded regions at both poles. The South Pole is a little more well studied, just because our resolution of the data with LRO is a little bit better at the South Pole. And that's just because we have a lot more stars at the South Pole than the North Pole. But as far as PSRs go, I believe the South Pole has those 3 really big ones. And the North Pole doesn't really have those really large ones. But nonetheless, you should have ice within both PSRs. And that has been studied a little bit, you know, to an extent, just not as much as the South Pole, which is why I focus specifically on the South Pole for this talk.
Okay, next question. What do you think is the most interesting question about the moon that has yet to still be answered? Like, what is the ultimate new unknown that's the new thing that people are wanting to find out?
Yeah. The next new question, I'm not really sure. Sort of the hot topic right now with the moon is the ice, what ice is there. And then applying that, how can we use it? After that, I'm not sure what the next hot question will be.
Okay, next question. What do you enjoy most about researching the moon? And what would you give somebody that, say, is in college and they want to go into that particular field? Like, what classes should they take if they're going into college? What professors should they talk to in order to get into that kind of field of research, etc.?
Yeah, so the science classes are really important. So are the math classes. Don't underestimate how much math you actually use in science and in physics. So those are the 2 big areas to focus on. Also, one area that gets overlooked is programming, coding. So all of my work is, you know, sitting at a desk and programming, creating all of this code. So yeah, that's what I do day to day, is just writing this code. So definitely don't overlook that.
All right, next question. What happens to the actual meteors that create the craters? Like, where do they go? What happens?
Yeah, so they these meteors are coming in, they hit the surface, they create this divot, which is the crater, and you know, they kind of get blown apart. They are all these little pieces that kind of go everywhere on the moon. So a lot of times, if you look at a crater, it's surrounded by this really bright region, and this is a ejecta that's coming out from the inside of the crater, but also, you know, like bits of the meteor that are getting scattered about.
Okay, next question. What do you know about the far side of the moon? And is it true that the lithosphere is thinner there than the near side?
I'm not sure about the lithosphere. So the far side, we haven't actually explored very much. You know, if you go outside and you look at it, we only ever see the near side of it. And all the Apollo missions were on the near side. But we do actually have at least one mission that actually went to the far side. I believe this was a Chinese mission. I'm not entirely sure on that. but I haven't, really kept up with it to know what all they discover there. So that would be, if you're really interested in what's on the far side of the moon. I know we did have a mission there at one point, so you can read up on that.
All right. We'll take one more question because we know we want to give Dr. Hooper a chance to be able to present and answer some of these questions as well. And we don't want to take too much of your time because we know you're incredibly busy. The last question we have here is do you think the moon is big enough to use gravitational lensing?
So I think it's actually too small to use gravitational lensing on. Yeah, I think it's just too small.
All right. Again, Lizeth, thank you so much for joining us tonight, sharing us your wonderful knowledge about ice on the moon. We hope to be able to send some more people your way if they have any questions. And thank you. And right now we're going to have Dr. Hooper join us and take over the presentation. Are you ready, Dr. Hooper?
Yes. Can you hear me okay?
Yes.
Okay, great. All right, I will start going back to...
Would you like me to introduce her, or do you just want to take it right away?
I'll just take it right away.
Okay. He's self-introducing.
Yeah, well, I'll do a quick introduction for myself. I work for the WEX Foundation, but I also teach as part of the Alamo Community Colleges. So I teach geology and astronomy with our local community college. But yeah, what I'll be talking about tonight will mostly be about work that's done through the WEX Foundation. And there on the first slide, you can see what the WEX Foundation is. It's a space STEM program. So we're interested in teaching the next generation of planetary scientists and educators and instructors and whatnot. So it's a space STEM program. So older folks like me are teaching the next generation of students. So that's what WEX is all about. And we're based right here in San Antonio. Okay, so many of you already know about the MARIA, but well, let me just back up and remind you what the title is. So I'm going to be talking about lunar lava tubes and the future of human habitation. So we'll see how instrumental we think lunar lava tubes will be for future human habitation and basically future human settlement. We plan to hopefully make these our lunar bases, or at least a good big part of our lunar base. And so when we speak of lunar volcanism, we're speaking of igneous rocks, we're speaking of what we see that's volcanic on the moon, and that's mostly the MARIA. So these are the most obvious volcanic features on the moon. So those are those dark splotches you see when you look up at the moon every night, like good night, like tonight. And they're basically composed of basalt. So these are basalt plains that cover about 15% of the lunar surface. And most of them are located on the lunar near side. And most lunar volcanism appears to have ended about 3 billion years ago. You occasionally see people arguing that maybe there's been some more recently, or maybe there's presently some active volcanism on the moon, or as well as Venus and Mars. But right now, really, the only type of volcanism we have going on in the solar system is what we have here on Earth, the volcanism we see on the large moon of Jupiter, Io, and then cryovolcanism on some of the other moons in the solar system. We don't believe there's any active basaltic volcanism going on anywhere else in the solar system other than the Earth and a type of silicate volcanism on Io. And then some other lunar volcanic features. So in addition to the MARIA, we have sinuous rills. There are a couple of different types of rills, but you can think of these as mostly being lava flow channels. And then volcanoes, volcanic eruptions build a variety of cones, ridges, and domes. And so we see some of those on the moon. And so here you see the Heracentius domes. So a couple of low relief little dome-like structures, and there you see a close-up of it. This is not a lunar sample, but it's your typical vesicular basalt. So all the little holes you see are from the gas escaping from what was once molten basaltic rock. And then, okay, so how do you form a lava tube? Well, to start forming a lava tube, you first need a lava flow. And then nature tends to channelize flow. So your lava flow eventually starts to channelize itself. And so it builds up basically its own little walls around the flowing material. And then as those build up, it starts to self-insulate. And that allows the lava to flow longer and greater distances from the source. And so that continues on. And eventually your lava flow, your lava channel may completely insulate and encrust and enclose itself, and you get a lava tube. And eventually the molten material will drain out, and you'd be left with an empty lava tube. And then if something happens to the ceiling, you poke a hole in the ceiling, basically, the lava tube collapses, maybe on its own, or maybe through a meteoroid impact, you get a skylight. So skylight, same type of word we use for skylights in homes, but you can sometimes get these little skylights. And in some cases, they can be pretty big, as we'll see coming up. So here's an overview of some skylights that we've actually now seen. Oh, yeah, I think the number of skylights and pits on the moon is now over 200, and there's many on Mars as well, usually associated with the large Martian volcanoes. So here are some skylights, pits, and tubes on the moon. The first two rows are on the moon, and then a couple on the bottom left there are some that have been found on Mars. And then there are similar occurrences on the Earth. And if you note they're enclosed in red, I'm going to be talking about Marius Hills. That's basically going to be our case study for this presentation. So we'll focus on Marius Hills. But that's what we mean by these skylights and pits. Yeah, so a skylight is basically a pit. As you can see in some of those, yeah, it looks like the roof caved in and you got an entrance into your lava tube beneath the surface. And so here's the Marius Hills skylight. See a couple photos showing where it is. So it's that dark open skylight or pit there in the Marius Hills region. And Marius Hills is located off in one of the Mare basins. And so it's on the near side. And then there's a little overview of the Marius Hills region. You can see a couple of sinuous rills, and you can see that the pit is located indeed inside one of these rills. And then here's, okay, it's showing very nicely. This is a nice little flight over the Marius Hills skylight that was put together by JAXA, which is the Japanese Space Agency, basically their equivalent of NASA. So there you can see the Marius Hills skylight, the pit. And you can see some of the surrounding topography. That yes, it's in a little bit of a channel. So it's a short video. And there you can see the channel. And there's the other rill. So if you wanted to find these lava tubes, focus on the rills, focus on the channels, focus on the old lava flows. And there it is. Yeah, about a 50-second video. So that's Marius Hills. And then the importance of lava tubes. Yes, why are these important? So this is a simple overview sketch that I drew out several years ago, kind of a crude little map, but it shows you in cross-section what we mean by these skylights. And so these skylights, these lava tubes, are very important for long-term human presence because they protect us from the environment. They protect us from surface hazards. So that includes radiation. So that includes not only the solar wind, but also radiation coming from across our galaxy and even beyond. So gamma ray radiation, etc. Protects us from micrometeorites. So being beneath the surface, you're obviously protected from the pitter-patter of micrometeorites. You would prefer not to have those puncturing your shelter on the surface. So if you go into a lava tube, you are protected from micrometeorites. Also, and some of the features shown on this slide we saw very well presented in the last talk. These lava tubes will also protect us from extreme temperatures, as well as some of the lunar dust. And so there in the little sketch, you can see the solar wind, you can see sputtering, outgassing, and impact vaporization. Again, a couple of topics that were discussed in the previous talk. And then there down in the lava tube, the way I drew this little sketch, I showed the rubble down at the bottom of the lava tube. If that collapse occurred while the molten material was still flowing, it would have been carried away. And then, is there condensation in these cold traps? Do these lava tubes act as a cold trap? Is there potentially water ice or other valuable natural resources in those lunar pits? We don't know. We saw a nice presentation in the last lecture about permanently shadowed or shaded regions. Well, these skylights, these lava tubes, basically are the same thing. So are these important little ingredients, these important volatiles, transported into these skylights and into these lava tubes, or they can be exploited as natural resources? We just don't know yet until we start exploring these. And then it also raises the issue of we want to be very careful when we first approach these and not damage the environment. I'll be talking about more of that more in a moment. But let me just give you a sense of the size, a sense of scale of the Marias Hill skylight. So here are a couple more photos. And note it's about 50 meters wide by about 50 meters deep. So roughly we're talking about half the size of a football field in width and about half the size of a football field down to the bottom of the lava tube. So the issue becomes, how are you going to get down there? If you're going to make that part of your habitat, part of your settlement, you have to safely get down there. And so that's basically engineering issue number 1 or 2. And some examples of lava tubes on Earth. I haven't been in a Thurston lava tube since I was a kid, but this is one of the famous examples of a lava tube on Earth. And so by studying these analogs, we can learn more about what we may find, or how lunar lava tubes, how they formed, how they react to their environment, etc. So this is an example of a terrestrial lava tube, good old Thurston lava tube in Hawaii. And then some other examples of lava tubes and their skylights from Idaho here. A couple of nice photos from the National Park Service. So you can see, yes, indeed, those are big skylights, and these photos look amazingly what we just saw with Marias Hills and some of the other examples. So you see that collapse. You see the rubble at the bottom, and you see the big skylight. And so now the issue is to get down to the bottom of the skylight, to the bottom of the lava tube, and then transport things that you need to set up a habitat inside that opening. And so one of the ways then to start accessing these pits, these skylights, is possibly with robots, using some sort of robotic access, and then using an autonomous zip line is one possibility. So something we've been working on for a number of years now is to set up some sort of little device that will go ahead and shoot basically a simple harpoon across the opening, across the skylight. And then that will allow you a way to transport material safely down into the pit. And so there you saw the little harpoon launchers in place. And with this one, you can see there, this has got the little track, so you can drive right up to the edge and then fire your harpoon across the pit. And then you can start working on deploying your equipment. And so I started also to talk about exploring these pits, and we don't know for sure what may be inside them. And so NASA is concerned about this, as are all the researchers and engineers. So we have in mind, of course, planetary protection. So an additional challenge then is to preserve these pristine lunar cave environments from damage and contamination. So if you land your spacecraft too close, you could possibly damage things within the lava tube. I think perhaps we did not appreciate how destructive landing a rocket could be near one of these. I think we've kind of looked at that question a bit more since the Apollo days and realized that, yes, indeed, these rocket launches and landings near such an environment could potentially disrupt it or destroy it. So we have to keep in mind planetary protection. And of course, new technology like robots could be used to enter these caves or pits in an unobtrusive way. And then once you get down inside the pit, inside the cave, inside the lava tube, and then you could go ahead and use, a variety of devices like laser scanning, etc., and start mapping out the interior. And so, continuing with lunar renaissance and reconnaissance and exploration, perhaps someday we'll be able to start using these lava tubes and start setting up equipment that we need for a habitat. And so this is just an image, an illustration done by XARC to look at the possibility of beginning to establish one of these as a lunar base. And here's just, whoops, why is it doing that? And then here's just another image. Hopefully someday we'll be able to carry out something like this and actually do this, but lava tubes are indeed the key to future lunar habitation. And then we are doing work like this right here in San Antonio. So here's some ongoing lunar caves research, analog studies being done right here in San Antonio. This is with our LCATS program, which I'll describe that in just a moment. But these are some students visiting Rubber Baron Cave. So you can see the students entering the cave, exploring the inside of the cave, using some instrumentation inside the cave. And there's what LCATS stands for, the Lunar Caves Analog Test Sites. And so this was one of our trips to a different cave. This was the Kickapoo Caverns back in March of 2019. So you can see some of the student robots. You see the one there has a little camera, a cell phone. I guess that's just a camera hooked up to it, as well as that red object that you see in the photo on the top left. That looks like about the size of a soda can because it's called a CanSat. So some of the instrumentation then is contained within that little CanSat. And you see some of the other robots. And so this is all practicing, getting us ready, getting the next generation of scientists and engineers ready to do this type of work. And then here's what we call our showcase event. So here's where the students have an opportunity to display some of the things they've learned and to kind of culminate their yearly activities by launching a high altitude balloon. So that's what you see at the top left, launching a high altitude balloon. You see some rocket launches. And at the bottom there, you see some future lunar construction methods being deployed and tested against the rocket blasting. And then in the bottom there, you see a simulation of one of the lunar pits. So that's, for example, a Marius Hills analog pit. You see a robot descending it with the CanSat attached. So all is a rehearsal, all good practice to study and research and to explore in the future these skylights and lunar pits. And then here's what you saw in the last slide right here. This was when that pit was basically still in the test stage. It's actually in the back of a truck at that point. And then we've found a permanent home for it over at the University of Texas, San Antonio. It's now in the greenhouse over there. And you can see how this was constructed over time. We built in some long tubes to simulate the lava tube, and then went ahead and placed on top of that some lunar regulus simulant. And then there you can see our little mock pit, and then the little robots crawling around on the mobility test bed. So all in rehearsal for doing this, hopefully someday for real. Okay, and at this point I kind of throw out a question. Instead of shipping parts and equipment to another planetary body, what can you do? So this is kind of mentioned a little bit earlier in some of the earlier talks this evening. If you're on, if you're on your lunar base, you just can't run down to the corner hardware store to get something you need, or if you have an emergency, it's going to be difficult to go to the local hospital. So you need parts, and you need to get them to your base, and you have to deal with constrictions of time. Space is vast. You're talking about, Mars is a long way away. Even the moon is 2 or 3 days away. Dealing with other planetary bodies that have different escape velocities. Anything that has to be shipped to another planetary body is going to be very expensive. And you have to deal with emergencies and unexpected contingencies. So how can you solve this problem? What if you need a part right away? What can you do? Well, I'll go ahead and kind of skip ahead to the answer, but maybe some of you are thinking ahead. And the answer would be 3D printers. And so 3D printing is one way to manufacture parts that you may need when you're off-world. Or this is also being done right now on the International Space Station. So 3D printing is a way to allow us to create these needed materials rather than having them shipped to the moon or shipped to Mars. And so on the left, you can see a 3D printer in action. And on the right is a model of 3D printed 3-level Martian habitat module. And so what you're seeing there are 3 levels of a potential habitat, and there in the center column, those are the doorways, the stairwells. So those are equivalent of a doorway. And so there you can see what this would look like with people actually occupying it. So there we have our little people for scale. And then you can go ahead and start filling in all the things you need for your habitat, the sleeping quarters, the laboratory space, etc. And then this is another example of how you could use this 3D printed process to manufacture structures that you would need either on the moon or also on Mars. And so this one, note that it has a curved shape to it. So this is the kind of the arc or curved shape habitat. And so something like that could be constructed by a 3D printer. And then you could fill in the rest of the needed parts. And then there you see at the bottom image, part of the gantry, there's a large 3D printer in action, printing out some larger 3D printed materials. And I also note there some of the shortcomings for a 3D printer. They don't print off equipment, they print off components. So you build a framework to which you add motors, electronics, etc. So we're getting more clever with how we can use 3D printers, but you can't print everything. But you can go ahead and print important key components. And then here's another example of a habitat that could be constructed by a 3D printer. This one called Hexab because it has a hexagonal shape. This is an example of one that could be constructed on Mars. And so this has the advantage of the fact that Mars has a thin atmosphere but does have an atmosphere. So your risk of being hit by micrometeorites is a little bit less on Mars. So you don't need to worry about covering up your habitat with, say, covering of lunar soil or regolith. But this just shows an example of possibly setting one of these up someday on Mars. And then returning for our lunar pit example, this is what an actual lunar base may look like. And we're probably realistically talking about the year 2050 or so before we really get to this stage. But this is what the setup would probably actually look like. Off on the top left there, you see the nuclear power zone, where there's perhaps going to be a buried reactor. Because one of the problems with the moon is, yes, you have solar panels, and those are shown on the left side of the figure. But the moon experiences 14 straight days of daylight, and then you enter 14 days of darkness. And so you need your power source to go through the entire lunar cycle of light and dark. And so a good way of doing that would be with some sort of nuclear-powered reactor. And then the habitation zone, so also shown there on the left, would be the entrance to your lunar pit, your lava tube. And then elsewhere on the diagram, on the right side, you see where the regolith would be used as feedstock into some of these 3D printers. And you can go ahead and print the components that you need for your lunar base. And then nearby would also be your landing pad. And then you could start burying your needed pipelines and other cabling and wiring that you would need to attach all the components of your lunar base. And doing such work is very difficult and involves many organizations, many people. So this is just some of the local and international teams that are all part of this type of work and that we've been working with. The LCATS program, which is a part of the WEX Foundation, UTSA. Also, you can also see the Scobee Educaiton Center has played a role in this, along with Southwest Research, and then many other organizations. And I mentioned XARC and showed some of their slides. That's a related organization to the WEX Foundation, and XARC stands for Exploration Architecture Corporation. And then I think I can stop there if anyone has any questions.
Thank you, Dr. Hooper, for that wonderful presentation. I definitely learned a lot from that. Thank you. So if there are any questions, go ahead and leave them in the question and answer bubbles. We'd be happy to answer them and or leave them in the chat. We would love to answer them. Are there any questions for Dr. Hooper? Okay, we do have one question coming up. Is it possible to fly a drone on the moon? Given that we're putting people on the moon, could you fly a drone on the moon?
Right now, based on our level of engineering, the answer would be no. There's just not enough of an atmosphere. It's going to be very challenging to do that on Mars, but NASA wants to put a drone, basically a helicopter, on Mars in one of the upcoming missions, and that is even going to be a challenge because helicopters rely on a specific and necessary denseness to the atmosphere, and right now the moon just has a very, very thin atmosphere, we call an exosphere. Mars is a little bit denser, and it's going to be a challenge to even get a drone or a helicopter to work to fly on Mars. So that's something to look forward to in the upcoming years to see how that project works. I'm interested in myself to see how it works.
Definitely. Another question is, since we are possibly going to have habitats on the moon, could we terraform the moon like we do with Mars, possibly?
With that last slide, I showed some degree of terraforming. In this case, just terraforming the surface, modifying the surface to what we need. Our landing and launching pads would need to be sheltered so it doesn't damage the rest of the habitat or the environment. But as far as actual terraforming the atmosphere, the moon is just too small. Doesn't have enough mass to really withhold, to preserve its own atmosphere. I know you mentioned what about terraforming Mars? Even terraforming Mars would be quite a challenge. Maybe someday in the future we'll be able to do it, but some of the calculations show that Mars just would lose its atmosphere too rapidly, quicker than we could basically resupply it. There aren't enough volatiles that we could basically release to give the atmosphere enough density to terraform even Mars. But, maybe those calculations are wrong. We'll see.
Well, here's hoping for the future. I got a question. What is your hope for humanity's greater perseverance in space, the moon and Mars and so on?
Well, it's long been talked about that we want to use the moon first as a jumping off point. And I think we're basically in line to do that. And maybe with Artemis and Gateway, we'll have a base which to jump off and to head on to Mars. I know there's a desire to go directly to Mars, and that may be what would happen. But realistically, we're probably looking at a step-by-step process before we get to the outer portion of our solar system. And to go beyond that, I think we're a long ways away. And to really go beyond the solar system and to travel to the stars, I just don't see how our little little bags of meat, our little weak bodies could really survive like something like that. So that may involve us having to evolve or basically turn ourselves into part human, part computer, part AI. That may really be the way that we can step beyond our solar system and get out to the stars, is that we have to kind of merge and evolve into a species that is part computer, part human. And I think that's still a long ways away.
Kind of reminds me of the old cartoon from the 80s. It's called Silverhawks, where they had humans that traveled that far and were part metal and part human. So interesting. Another question coming in. When was the first lava tube discovered?
The first lava tube on the moon was discovered just a couple years ago by a team of Japanese researchers. It was maybe 6 years ago. I don't have the date at my fingertips, but yeah, it was only a few years ago. They had been speculated about, but the first time there was convincing proof that one existed was only fairly recently, 5 or 6 years or so.
Okay. Next question. Up to how many individuals could a lava tube habitat support?
It's really going to depend on the size of the lava tube. If you saw some of those photos I showed with limestone caves here in Texas, you're not going to be able to get very many people inside of those. But the ones on the moon and Mars seem to be an order of magnitude larger. So I probably think first order number would target about 100 people, and then work on expanding it beyond that. I think a lot of these early habitation goals, early colonization goals really call for about 100 to 1,000 people.
Cool. Do you believe that there are life on other planets?
Other planets, yes, within our solar system. I want to see it before I believe it. But we've now discovered more than 4,000 exoplanets. And so far, none of them seems to meet all the requirements of our good old Earth. But I think sooner or later we'll find an exoplanet that probably does have life on it. So yeah, I think there's life out there somewhere. And even in our own solar system, I think we're kind of wrong in thinking we're going to find fish, we're going to find trees, we're going to find birds, mammals. We have to think more extremophiles. We have to think more along the lines of organisms that exist in extreme environments, and again, what we call extremophiles. So it's quite possible there are subsurface oceans on moons like Europa, maybe Ganymede, Enceladus, and it's possible there could be life under the ice in the water on some of those moons. But proving that is still going to take a bit of engineering that we don't have the handle on yet, because we'd have to drill down there to discover it, and that's not an easy task.
Definitely. So a general question for you. If you have a young, inspiring person who wants to do what you do, what would you recommend, and what steps should they take?
Of course, going through high school, take a lot of science, math, engineering courses, and then pick out a college or even some of the good high schools to get you started that specialize in STEM education, and use that to get yourself started. And then find a school that does what you're interested in doing. And if I was to go back and talk to my 18 or 21-year-old self, I would say, instead of being a typical quiet, geeky scientist, I would say, hey, you got to communicate more. You got to get out there and meet some people and talk about yourself a bit more. I did not do that very well. So I think don't forget about networking. Networking is very important. I think it would probably be good to find internship programs that would help me get into the Smithsonian. I started at the Smithsonian on an internship, and then ultimately ended up getting hired at the Center for Earth and Planetary Studies, where I worked on and off for 10 years. Probably should have never left, but I left to go get my Ph.D. So I would do that, yeah, and definitely consider internships, and definitely work on networking and practice your networking skills.
Okay, are there any other questions? Well, if there are no more questions, thank you so much, Dr. Hooper, for your wonderful knowledge and for joining us here tonight to share what you know and to inspire possible future generation of lunar enthusiasts.
Well, you're quite welcome. Thank you very much.
All right, so just to kind of wrap up things here, one of the things I wanted to show you folks before we head on out is, if you folks are interested, you can purchase a moon for your kids. So if you're looking for an awesome Christmas gift for your kids, this is called The Moon in My Room. And you can turn it on and you can see the display of the moon. But the other fun thing about this, it can go through the phases of the moon. So if you're looking for something to get your kids for Christmas or as a fun little night light that doesn't abstract them from being able to sleep, that is definitely something you can do. All right, if you'll just bear with me for just a couple of minutes, what I'm going to do is I'm going to zoom my telescope in towards the moon and give you a live view of the moon and show you some of the craters and details. So just bear with me just a minute. All right, so what I have done is I've connected my laptop to my telescope. I'm sorry if the moon is drifting a bit. I'm trying to work on the tracking because I'm just now seeing stars and I couldn't be able to align with some stars in order to be able to show you some of the moon. But now you can see some of the details of the surface of the moon, the dark areas of the Maria, and you can definitely see more details by looking at the moon. So hang with me and I'll bring the moon back. So we'll slowly let it drift into the view of the telescope. So the line that you're seeing right now is what is known as the terminator line, the day and night line. So if you look on the edge of that line, you'll start to see some craters start to appear. And those craters, you can start to see some of the shadows in the area, kind of give you an idea of how deep some of these craters are. So are there any last questions whatsoever about the moon? Any details? We'd be happy to answer them. Well, if there are no more questions, we just want to say thank you all for joining us for International Observe the Moon Night. If you can get a chance, go out, check out the moon, do some of the fun activities with your kids, do some amazing things to check out our closest celestial object. Until next time, stay safe, stay healthy, and always never stop learning. Have an awesome night, folks.